let's see that right. Everybody come back down to the front. Okay. What the heck is going on here? This is a difference engine. What does that mean? Well, let me go back and talk about why it was needed, and then we'll get into the theory of how it works. This goes back to Charles Babbage. And he was born in England in 1791, and he became a mathematician. Really genius level guy. He not only dabbled in mathematics, but as you can see, he was a fantastic engineer, inventor, really, I guess you could say, kind of a Da Vinci man, you know? During his life, he not only thought up these amazing machines, but he also invented stuff like a cow catcher to go in front of the locomotives, a chart recorder to monitor the condition of the rails, an accident recorder, a black box to go in locomotives, theater lighting, different kinds of colored theater lighting. He built his own RV to tour Europe. Amazing job. And what happened is he had, while he was a genius personality, that's the good news. The bad news is probably that he was a genius personality. And if you've met any people like this, they can have some personality quirks, right? And Charles Babbage was not alone, but he certainly was a difficult personality. If he liked you and considered you a sort of peer, you could come to his house for all kinds of parties and all. He probably had Charles Dickens in his house and Charles Darwin, people like that. But if he disagreed with you, you either got him face to face, and you may have met people like this that would get into an argument with immediately when you start a conversation, or he would send you a nasty letter. It's just a good thing he didn't have email. And this really got in his way during his lifetime, periodically. He just couldn't get things done. To give you an idea of that personality, I'd like to quote from a letter he actually wrote to a contemporary of his named Alfred Tennyson. Seems he didn't like one of his poems. So he wrote this letter. It says, "Dear Sir, in your otherwise beautiful poem, The Vision of Sin, there's a verse which reads, 'Every moment dies a man, every moment one is born.' It must be manifest that if this were true, the population of the world would be at a standstill. I would suggest that the next edition of your poem you have it read, 'Every moment dies a man, every moment 1 1/16 is born.'" The actual figure is so long I cannot get it into line, but I believe the figure 1 1/16 is sufficiently accurate for poetry. Can you imagine Tennyson opening up this letter? Like, who is this wacko, right? So this is just, but it does show two things. One, that he had a personality quirk, but two, he had a real need for precision, didn't he? He wanted things to be accurate. And so what's happened in his early career, in the late 20s, 1820s, he and a buddy are looking at books of mathematical tables. Now, for those of us that are too young to know that we didn't have computers on our desks all the time, we had to do calculations with slide rules, mechanical calculators, and books of tables if we had to look something up. For example, one that Babbage was looking at was common logarithms. These are tables that help you multiply and divide a lot by just adding and subtracting. Very much easier than actually multiplying. They're very handy. And he and a buddy were looking at books of tables and comparing one publisher's version with another. And when they compared it number for number, what do you think they found? Huh? There were differences. Somebody was wrong. And this got Babbage very, very excited because he knew that England is in the middle of the Industrial Revolution. And they're building railroads and locomotives and big knitting mills and bigger buildings and bridges. And he said, well, oh my God, one of these things is going to be a disaster because they used the wrong number. And he had the need for precision. So he says, we got to recalculate these numbers without error. He knew there are many sources of error at that time. Now, the method they used for calculating these tables was called finite differences. Here's the mathematical principle. Let's say you wanted to make a table for the function sine. This is a sine wave. You're all familiar with that? So the function sine, what happens is, I can't compete with that. Function sine, let's say you want to make a table of these values. Well, what you would do is you come up with some sort of mathematical equation, it's called a polynomial, that models the function very closely throughout most of its range. Once you have that polynomial, you can solve it for it a few times manually, and then for every succeeding value of the unknown, let's say x, bottom, you just have to add certain differences between the values of the equation. So you don't have to square things or cube things or multiply, you just have to add. So he said, one of the problems is people are using this method to make the tables, but what they're probably doing wrong is that when they write it down, they're writing it down wrong. Or they may have added wrong. And then when they have all these thousands of numbers calculated, they hand it off to a printer. So how did we print back in the 1820s or 30s? With movable type, remember? Mirror image, set each number with a piece of type. Very easy to make a mistake. So he says this cries out for some mechanized solution. And he sketched out the idea of making a difference engine, something that would be a fancy adding machine that would do these tables. And he built a little model in the 1830s. He showed it around in his house, people at his parties. And then he decided we got to build this machine. So the next thing he needed is what every entrepreneur needs when they have a good product and want to sell it, which is money. So there weren't any venture capitalists around then, but he went to the Crown, and the government funded the project. The next thing he needed was a really excellent machine shop. He found a nice tool maker in London, and they started to build the parts for what we call difference engine number 1. Now, that engine, this is difference engine number 2, his second design. Difference engine number 1 would have required 25,000 individual parts. 25,000. And they started, and they argued, and they worked, and they fought, and then so on and so forth, so that 10 years later, he only had 1/3 of the parts built. You can imagine his funder, the governor, was running out of patience, and the machinist he was always arguing with, they had a sort of separating argument. They couldn't get along with each other. So difference engine number 1 ends, and it never gets built. But during that 10-year period, what Babbage had been doing is working on a design for a real full-up computer, not a difference engine. It's called the analytical engine, and it's a masterpiece of mechanical engineering. And we know it was a computer because it had memory, a processor, an input-output section, everything you need to make a computer. It even printed. He worked on that through his entire life. But in about 1847, he turned around again, and he said, I think I can now simplify the difference engine. And he drew up the drawings for a machine that only needs a mere 8,000 parts. And he offered it to the government. Says, I owe you guys, you know. And they said, no thanks, Charles. We're past that. So none of these amazing machines ever got built. Babbage died very embittered, very sad, depressed about the fact that he didn't change the world when he knew he could have. Okay, we fast forward now. The drawings of this machine wind up in the collection of the London Science Museum. We come to 1984, 1985 period, where they have a new creator of technology, a guy named Doran Swade. And Doran Swade says, how will we ever know if Babbage's design would have worked unless we try to build it? And this puts them on a big, long odyssey of figuring out how to do that. They need drawings, they need engineers, they need machine shops, they want to do it authentically, etc. Well, it turns out that they wanted to finish the machine by 1991. That would have been Charles Babbage's 200th birthday. What a great monument to the man. Turns out, by 1991, they just had the calculating section built, where Mike is standing to right here. And it worked. It actually does calculate correctly. And to prove that to you, we're actually calculating common logarithms today for a table of common logarithms. The equation, it turns out, that's being solved using this finite differences method is this little guy right here. We couldn't fit it on. We need a big chart of this, but it's got big, long coefficients. You can see the x to the 7th, x to the 6th, x to the 5th. You wouldn't want to sit down and solve this equation a couple of thousand times. So using finite differences is the way to do it. So right now, after Mike did those cycles he did when you were looking at the machine, it solved, the last log solved for on here is the log of 1.5330, since this is the result column right over here. 1.5330. Now to show that it's right, we used a computer, a modern computer, to evaluate that. I'll let this lady hold this chart. I'm going to read the answer off the machine for 1.5330. Okay? It better be this number right here. Okay? If it is, let us know. All right. It looks to me like 0.1355422. Did I miss the 0.18? Sorry. Yeah, 0.18, right, it was behind the wheel. 0.1855422. Okay. So it's doing good. So how does it do this? Well, what you're looking at here is these 8 columns of number wheels. You can call them registers if you're a computer person. Each column has 31 number wheels on it. And what happens is, after we calculate these finite differences, and we'll do that later together to show you how it works, we get all these numbers, we're able to free up these columns of wheels and turn them to these initial settings. Right? We then lock up the machine and start to crank. And as Mike cranks, this column is added to this column, and so forth across the machine, just adding up. And you can see that in between each column is this huge gear stack. So let's say one of these numbers has a 4 on it. The gears would rotate 4, 3, 2, 1 back to 0. At the same time, it's engaged with its partner on the next column, cranking it up 4 digits. Got it? So it's an addition process. And then these gears disengage from the column it just added to, but stay engaged with this one in order to put it back where it was. Because you just set it to 0 and put it back to the initial difference. So that addition takes place across the machine until we get an answer here. Museum said, it's great, it's working. But this is probably the most important part of the machine, because Babbage didn't want any errors. What this does is, after the answer is here, it is put up with these rods and gears and stuff to rotate these number wheels in here. It's actually typed in here. It's rotated to the solution. Ink is smeared on the type, which we won't do today because we don't like to clean it up. There's an ink well here. And this paper is brought up to the type to print the answer. Even more important, this tray down here, this bronze tray, it would be filled with something like plaster of Paris. There are more typefaces. They're rotated to the answer. They come down and press into the plastic an image of the answer. It's pulled up. The tray automatically increments inward. Again, it rotates. Again, you get the next answer, and then the next answer, and then the next answer. When a column of data is filled, the tray automatically zooms out, moves over, and we start the next column. What are we making here? Huh?
Making a print.
Well, we're making a mold. We're making a mold for a printing plate. The printer takes that mold, pours lead into it, and there it is, no movable type. So that eliminates that error. Everything's perfect. Well, the museum doesn't have any more money to make this thing. This has got almost as many unique parts as the rest of the machine. Now, Providence strikes, though. They get a visit from a guy named Bill Gates. And Bill Gates says, I got a chief technical officer, ex-chief technical officer, by the name of Nathan Myhrvold. Nathan, he's a serial entrepreneur, he's a collector, and he's got money. They get in touch with Nathan, and Nathan says, oh, this is great. I'll tell you what, I'll give you money to finish that first machine. And if it really works the way Babbage said it would, I want you to build me another one for my own personal collection. So you're looking at serial number 2. There are only 2 in the world. This is Nathan Myhrvold's difference engine number 2, and he says every year he lets us keep it another year. So far, to show it to you, he says that someday, maybe when he retires, he's going to take it up to Seattle and stick it in his living room. So it weighs 5 tons. Mention the size, but he's got a big living room. So that's how we have to have it here today. So now that you know all that, we'll let Mike crank it again, and I want you to watch and listen. So you can watch as these gears do the addition. It happens in 2 half cycles because the machine is kind of what we call pipeline. You'll see this column add to this column, then you'll see this column add to this column. Add the odds to the evens first, and then add the even columns to the odds second, but the addition takes place across the machine, and then you'll see the print cycle. You will also hear a loud clacking noise. Babbage had to make doggone sure that these gear wheels, when they're free, don't move a little past where they should be. They've got to be all in line, because if they're not, when this gear stack comes back in to add the next one, it's going to jam. Right? So these big, huge blades, you can see only the bottoms of them, that run all the way up the columns, come clacking in, realign the gears, and pull straight out. And then they're free to turn again. So watch and listen. And by the way, to show you that Babbage thought of everything, it just boggles the mind. When this tray is full of numbers of solutions, you better stop, or you're going to overflow, right? You're going to miss a solution. How does Mike know that? He's way down there cranking. Well, there's a little cable here that's got a weight dropping into a tray at this end. The cable runs on the bottom of the machine, comes up here, across to here to this little pole. As soon as the tray is full, it's going to yank on that pole and shut off the machine. Disconnect his crank. That tells him he's got to put in a tray. And by the way, there's 2 trays. One that makes a book about this size, and one that makes a big book like this. So that happens simultaneously. All right, let's go. Let's do this, and we'll watch it all happen. So you can see how the gear stacks kind of jog up and down, so they can engage, add, disengage, restore. With the print, the tray is moving into it. Here's another print. Tray moves inward. You'll notice one other interesting thing, that Babbage did not like springs. The only place springs. We didn't use springs any place except at the top of the columns to kind of counterweight them so they'd be easier to lift. But in terms of the calculation, he didn't think springs were reliable. Really not. They wear out. But so you can see that when Mike turns the crank, the basic function, all the functions of the machine are sort of programmed by these cams here, these odd-shaped wheels. And they're in pairs. Normally you would have a follower on the cam that has a spring that goes in and out as the cam changes shape. Instead, we have mirrored image pairs of cams. So there's a positive action on everything. Right? So the guy was quite a brainiac. All right, let's go around the back and look around the back of the machine. Okay, what's happening here? Now, as you pass by this side, you'll see a lot of gears and wheels and stuff. It's for variable formatting. You can choose how many numbers you printed, how you spaced them, how many columns on the page, and so on. All 130 years before Microsoft Word. It's amazing. All right, come around. Watch that pillar pretty tall. So, Mr. Babbage had another challenge that he had to solve. When you are adding, you guys have two rows of numbers, you want to add them. You add the first two numbers on the right together, and the sum is more than 9. What do you have to do? You have to carry. Now you do it, you don't even think, right? 9 and 6 is 15, carry the 1, write a 5. What Babbage knew was that a lot of calculators that had been built in the past used various ways of pushing the dials to carry, and friction became a problem. Some of you may remember that the old odometers in the car, where you had physical wheels, there's a little bump on one side of one wheel. As it comes around, it counters a bump on the other one and carries it forward. When you get to 100,000 miles, sometimes the odometer freezes up because it can't push all those wheels simultaneously. So Babbage wanted that. He also wanted a very efficient method of carrying. So what he decided to do was to do all the addition first and then carry as a secondary operation. If you guys want to add numbers that way, you can. You can write 9 and 6 is 15, write down 15, next column, and then do the carrying right to left, and you would get the same answer. So here's what happens in this machine, which is astonishingly amazing. As one of the wheels goes from 9 back to 0, it pushes out a little lever here on these bronze column. They're called carry levers. What it looks like in detail is here under my index finger. See, it's a little fragile looking little piece of bronze. Now what happens is, when the wheel goes from 9 to 0, it pushes this lever out slightly in a counterclockwise direction. It's called the carry warning. So over here you can see a little pop out of the lever. That puts this arm of the lever in interference with these push rods that are on this column. When it's time to carry, we pull the register from the bottom to the top, least significant digits to most significant digits, and if that lever comes around and this is in the way, it's going to push on it. When it pushes on it, these little teeth down here are going to move the wheel just above it by 1 digit, accomplishing the carry. And the reason we pull from the bottom to the top is you would be pushing that next wheel from 9 to 0. So you have to carry in sequence. Got that? Okay. What we're going to do is crank it. I'm going to put my finger as close as possible to show you what's happening without losing it. And if you remember, the original equation had a ton of negative coefficients. See, there's some minus signs over here in this column. Well, this machine doesn't know from minuses, negative numbers. The only way you do a negative number is with tens complement. So minus 1 is all 9s. You add 1 to it, that's 0, right? So there'll be a lot of carries in the odd column, especially this one and this one over here. So if you watch closely, the first thing will happen with my cranks is these will all be reset inward, and then it'll pop out just a little bit. It says carry me, and then boom, it'll be carried as the levels come around. All right, let's do that. Watch the column. There's the reset. Carry one in, and you carry straight up. Watch again. This one a little bit. Carry one in, whoops, carry. Can we see that? I don't know how we thought this up. Carry one, whoop, after instantaneously over there. Carry one in. Okay, any questions about the carry method? Great. All right, come around here now to this blackboard. Do not be afraid, we're going to do a little algebra together. All right, how do we get those initial numbers? How do we get the differences that are put on those columns to start off with? Here's a really simple polynomial. Result equals x squared, which is what? X times x, plus 1. The first thing you have to do with any one equation is to solve it one more time than the highest exponent in the equation. So we have to solve this one 3 times manually. So let's do that. So if x equals 0, what's the answer? 1. If the x is 1? 2. Yep. If x is 2? 5. Right. 2 times 2 is 4 and 1 is 5. We now subtract the first result from the second. We put it in difference column 1. Second from the third, difference column 1. Right? And we now subtract these first 2 differences. Put it in difference column 2. You can kind of see that if I had a third order equation, I'd have to go down 1 more to get this 12 over here. All right. Now, with some adjustment for the fact that there are two half cycles, I would just use the first 3 different columns of the machine from the left. The result column, the first difference column, and the second difference column. Put these numbers on it. Manually turn it, lock it up, and then we begin to crank. The machine says 2 and 3 is 5, 5 and 5 is 10. The answer for x equals 3. 2 and 3 is 5. 2 and 5 is 7. 7 and 10 is 17. The answer for x equals 4. 2 and 7 is 9. 9 and 17, 26. The answer for x equals 5. You just keep cranking them out that way by just adding. Got that? That's called the method of finite differences. Okay, all right. Back and wind this up. Now, of course, somebody had to solve this equation before we could do use the machine to do what it's doing today. Somebody had to solve this equation 8 times. And it's not easy, is it? All right, so now, lastly, before we do one more crank here, what's the position of Charles Babbage in computer history? Well, there are a lot of books written on this, and I read a few of these, and I will tell you that we honor him as a great man, a great inventor, a mechanical genius, but not only that, he really advanced the state of the art of manufacturing, because the idea to make such repetitive parts and to get them all right, he had to, come up with a lot of ways of making these parts with precision. So he sort of pushed along the mechanical manufacturing process. But my view is that had he made the machines in his time, he may have advanced computing technology by decades, especially the analytical engine. But he didn't. It's the same example as somebody like Apple coming out with an iPhone, right? It's a revolutionary thing. And now we have tons of people making different iPhones with different operating systems doing different things. So once you have a revolutionary idea, a lot of people grab it up, but he didn't. So we still honor him as a great guy. In fact, there is a website called plant28.org where people are actually thinking of maybe trying to build his analytical engine. And that would fill this room. Amazing machine. It would be great if it ever gets built. If you're interested, you can go and look at that. I think it's the biggest problem that we'll have with that is that Charles Babbage never stopped designing it. So this is a common engineering problem. Get the engineers to stop designing and start building. But I'm sorry if there are any engineers here. I'm one also. Anyway, that's about it. I want to tell you one more thing. He had a protege, female named Augusta Ada Byron. She was the daughter of Lord Byron, the poet. She's very young. She joined Charles Babbage in some of his work. She married a count. She became the Countess of Lovelace. But her thing was math. And we know from some of her writings that she foresaw a lot about computing. She knew that these numbers on the machines could be not just numbers, but characters in the alphabet or symbols, and used for other various things in the world. And she was very bright. Unfortunately, she passed away at age 36 from cancer. If you're interested in Babbage and Lovelace further, there is a DVD in our museum store called To Dream Tomorrow. It's very, very interesting about their lives and very well done. So that's about it. I think you know. Do you have any questions?
I think she's featured in Isaacson's new book. Which
okay.
I think there's a
and in The Innovators, yes, which is in the bookstore, in the museum store also. So, yeah, I mean, they named the computer language after her in the middle of the 20th century, Ada, ADA. So, that's still used today. All right, any more questions? Sir?
I do. When the guys in London went to physically create this, how much engineering did they have to do?
All right, that's a great, well, a lot. That's a great question. Well, Babbage's drawings were very, very well done. A lot of the detail wasn't as obvious. And a lot of times they came across a mechanism like this carry mechanism, and until they built a model, they didn't really even understand what was really going on. The other thing was that if you're an engineer and you design something and you never build it, you think it's 100% right? No, it's never 100% right. You find problems with it and you fix them. Would Babbage have found problems with the difference engine when he went to build it? Yes. Did the museum encounter these problems? Yes. What did they do? Well, they had an authenticity committee. And they would say, Babbage would have found this, and he would have fixed it. Or if the principle of the whole machine was wrong, why build it? Right? So there were things like that in the machine. One easy one, Babbage had never really designed the frame for the printer mechanism. His drawings kind of show it hanging in space. And fix that. The other thing is, he was going to crank it from this top gear over here. One solution per revolution. But Mike would encounter 4 times the force he's putting into this right now. You get really tired really fast, and it'd be tough to maintain the rhythm. So the museum added a 4-to-1 reduction gear. So it takes us 4 revolutions of the crank to get a solution. There are little things like that. Any more questions? All right, well, if you have some, hang around. Mike and I will be here for a few minutes. If anybody still wants a tour in Revolution, I'll be giving one of those starting at 2 p.m. We'll meet in the lobby just outside the Revolution entrance. And thank you very much for your attention. Thank you. Thank you, Father.